Yeah, it's a really nice last question in the junior A level. It's got a bit of combi, algebra. I don't know if it has number theory, but like, so you got 99 cards, okay? And the total sum of the 99 cards is irrational, okay?
Yeah.
And you want to have this thing called an unfortunate pile, which is, it's not just the whole sum is irrational, it's every sum, every part of that sum up to the whole sum is irrational. So if you add up any portion of the cards from the top, it'll also be irrational. And then the question is, how many ways? What's the um what's the least number of ways you could have an unfortunate pile by permuting your pile of cards? Okay. Okay. So this is a nice solution. I think I basically got this idea from Rayden's solution again, um, but probably fixed up so it's easier to understand. Um, so the answer is 98 factorial. Okay. And so you can get 98 factorial by having just one irrational card, so like a root 2, and every other card is rational. Okay? So like 1, 2, up to 98, say. Okay? And if you want to make an unfortunate pile, you need to put the root 2 at the very top. Okay? Because otherwise you get rational sums. Okay? And if you put the root 2 at the top, obviously every sum will be irrational because it'll be root 2 plus some rational. Okay? And so the total number of ways of doing that is 98 factorial because it's the number of ways of permuting these. Okay? The number of ways of ordering 98 things is 98 factorial. Okay. Now explain why you can't get any less than this. Why is that the least number? Okay? So we're gonna call the cards and their values a bit to x1 up to x99. Okay?
Can't it be like 0?
What can be 0?
Like the number. Yeah.
What number?
It's like if they're all rational.
No, the sum has to be irrational. Yeah?
Like if there are 0 numbers that could be irrational, that one could attain.
Okay, you just didn't listen to what I said just then in response to you. The whole sum has to be irrational. So there has to be an irrational number.
Oh.
Okay, so here's the idea. So if we take so the total number of permutations is 99 factorial if we just counted all of them, right? So if we can show that 1 in 99 of them has to so at least 1 in 99 of them has to be unfortunate, okay? Then we get it has to be at least 98 factorial. Does that make sense? Okay, so for every permutation, so if you have a pile of cards, okay, so 1, 2, all the way up to 99, okay, you can always cycle them, okay? So cycling means you kind of move them down like this, yeah? So you just keep cycling them around, yeah? So can you see the number of ways you can cycle it is 99, yeah? Because you can have you can have everything go all the way up to the top, and then finally it'll come back to 1 again, yeah? That's why it's called cycling, because it's kind of like going around in a circle, all right? Okay, so what we're gonna show is that not every single one of those cycles can be not unfortunate. So one of them cycles has to be unfortunate. Does that make sense? And since there's 99 of them, okay, and everything can be that gets also like 1 in 99 of all the permutations as well. Does that make sense?
Yeah.
So if we can show at least one of them is unfortunate, then we're done. Okay? So we kind of same like the argument Daniel had. We suppose all of them are not unfortunate. Okay? Does that make sense?
Yeah.
So if all of them are not unfortunate, so this one's not unfortunate, right?
Yeah.
Okay, that means at some point at the start, we're gonna get like the sum is gonna be rational. Okay?
Yeah.
And we call this sum S1. Okay? Does that make sense? Okay. And now, if that's the case, let's consider the pile where the first number is the next card. So xk1 plus 1, right? That's also not unfortunate. So there's also going to be some sum up to xk2 and call that s2. That's also rational, yeah? So the rational is a q, okay? So these two things are rational. Does that make sense? Okay? And we can just keep doing this. Can you see that? Because then we take the next pile, and it's not unfortunate. There's going to be some sum that's rational. Yeah, you can call it S3. Yeah, and we keep going. We keep going until basically this um fits nicely together. So like obviously once you get to 99, what happens? You just go back to 1, right?
Yeah.
Okay. So you keep going, but it might not hit 1 exactly, right? It might not just stop there. It might go all the way to 2 or something. Does that make sense?
Yeah.
Okay. And then you go from 3 something and then you keep going, right? Okay. But if it does stop at 1, then that's good, okay? If it stops at 3, you just keep going, okay? You basically keep going until it stops somewhere where just before it has started before. Does that make sense? So like the places where it stops are like xk1, xk2, xk3. So if it ever stops at xk1 again after a full revolution, yeah, does that make sense? Then you get a multiple of everything. Does that make sense?
Yeah.
So like if I go all the way around, I go all the way around to 1, I go around once, right? And then but then I stop like here. Um then what happens is I can combine, so I can pretend, so if I ever stop like here, right? Then I can pretend I started from here, right? And then it went all the way around a whole number of revolutions back to here. Does that make sense?
Yeah.
Does that make sense? So what do I get? I get I get x1 plus x2 all the way up to x99, right?
Yeah.
That makes sense. And actually, I feel like you only get one of them, right? Even though I think I remember someone saying you get a multiple of them. It's just one.
No, you can get more.
But you get multiples?
You can because if you think about looping around, if you loop them multiple times before you reach the point where like you end, then
Oh, okay.
that would be like an integer multiple. Like you.
Okay, so you might not get it on this first round.
Yeah, you might.
You might have to keep going, but eventually it has to get something because there's only 100 places you can stop, right? Does that make sense? So if you loop it 100 times, you're gonna have to stop at some point. That's where one of the things is stop before. Yeah.
Well, see, wow, Jason is so ass at right. Like, okay, I see now his proof. Okay, I see it now. Wait, I swear to God, this writing did not say that.
Yeah.
Okay.
This is I got this from Rayden, not Jaden.
I know.
Yeah.
But I was just reading Jaden's proof.
But I read Rayden's first, so I had more of an idea of what was Jaden trying to say.
No, I now understand.
Okay. Does that make sense? So you're just kind of going around and around, yeah? Does that make sense? With this condition, okay? And you go until you end up at the same place you ended up once before, yeah? And when that happens, then you can kind of pretend you started just before you ended, and that will go a whole number of circles around, right? Does that make sense? So then what you get these S1 plus S2 plus up to like Sn, right? Is equal to x1 plus x2 all the way up to x99. So you get everything around the circle, and possibly some multiple of times, okay? Does that make sense? Okay, and we know these are all rational, yeah? So if these are all rational, the sum is rational, yeah? Yes? And we know that this is meant to be irrational, yeah? Okay, and then we know y is an integer, okay? Or it's a natural number, okay? That makes sense?
Yeah.
Okay. So can you see there's something wrong with that? So we have an irrational number times an integer is rational. It's not possible because you just divide by y, right? Because this number is like some a over b, yeah? And you divide by y, you get a over by is not rational, yeah? Understand?
Yeah.
But that's the definition of basically rational. It could be written as a fraction of integers. So it's a contradiction, right? So not every cycle can be not unfortunate. There has to be one thing in the cycle that's unfortunate. Does that make sense? And then you're done. Okay. All right, guys. Thanks for listening.
You did? Oh, yeah, fine.